So this is the list of things that I said I was going to talk about, but then I realized that this is probably too ambitious. So we'll see how we do. My hope is to just get through number 2, and then we can always do 3 and 4 in another week. So it's just kind of a little bit of an outline. So I'm going to start out with a brief review since we haven't been together for a couple weeks, and so this is kind of the come on in. This is kind of the brief review, and you guys know about a lot of this stuff already, and this is the kind of basic mechanism that we've been using. Enzyme binds to substrate, makes an Michaelis complex, and then that reacts to give enzyme plus product, and those were the 3 rate constants that we were using. We're going to just continue to use this pretty simplified mechanism for today, and then when we get to the kinetic shortcuts, we'll start to add in a more realistic scenario, because we know that ES reacts to give EP, and that step's reversible, and then it can release product, and that's reversible. But we're not going to worry about that yet. We'll see later that we can handle that and simplify things back down. So, so the last time that we got together, L2, lecture 2, what we did was to, I'm going to find a place for me to sit. Let's just try sitting here for now. We wrote down, again, basic rate law, which is given here. This is a little thick. Okay, and that is, rate is just the rate of formation of the product with time, the product over here, P. And we can just write down the rate law for that, because it's only formed by one channel, and that is K2 times ES, this part right here. And so that's what we end up with there. And we saw that we can also think of the concentration of ES from this relationship here as, and I haven't figured out how to get rid of the flickering. I tried all sorts of different things, and then as a last resort, just now I emailed to help people, and they said 24 hours. I Googled it. I turned off all sorts of things on my iPad. I turned off my firewall with Semantic, and none of it made any difference. So, and the good news is that when the recording's made, it's not doing that. And I think as a last resort, what I could do is just plug my iPad directly into the projector, but then I wouldn't be able to move around with it. So I'm hopeful they'll help me fix it. But we used this definition over here, and we saw that this was really powerful, that we could simply define fraction ES as ES over all E species, where we could sum these guys up, and then we could use a partition function type of analysis. And so when we replace ES by FES by E naught, we end up with this form here, which is K2 E naught times fraction ES, or VE, this final form down here, which is that V equals V max times the fraction of ES. And probably nobody has ever really, I'm guessing, looked at enzyme kinetics in that way. But I really like that way of looking at it. So if you just think about it for a minute, one is we showed it was a powerful way to derive new equations, and we derived substrate inhibition in different ways. And we're actually hopefully have time to go back and revisit that. But it's also a powerful way to think about enzymes. So look, I always like to look at equations and kind of let them talk to me, and I will try to write them in different ways that help me think about it. So there's lots of ways to write equations out, right? And so when you look at this particular reduction of the equation, what you see is that the velocity can go up to V max, and that it's kind of tempered by the fraction of the enzyme that's in the ES complex. And if that fraction goes to 1, you're at V max, and if it's less than 1, you're less than V max. So it intuitively makes a ton of sense, and we derived it. And we also found that it's really powerful for deriving stuff, because all we need to do is rederive the fraction of ES, and we can always get that as ES over the sum of everything else, and then we can treat that in a partition function way. So that's my brief review. I don't know, does anybody have any questions on anything? Let's just keep going on. Okay. So, so what we're going to do now is look at kcat over km, and it's a really important concept. And I guess Josh, I see you over there. Also, particularly wanted you and Scott to see this part because it has a lot of importance when you're dealing with competing substrates. So if you have two substrates and you want to know which is better, or you do a combinatorial experiment and you have a million substrates and you want to let them compete with each other and you want to know which is better, that's what this is important for. So it has a lot of biological import to it. So again, here I just have the model that we've been using. Back in lecture 1, we used the steady state assumption, although in lecture 2 we use more of the partition function analysis. And remember, the steady state assumption is simply thought about in this way, which is that the enzyme substrate intermediate isn't changing with time. And so when we write down the rate law for ES, now you can see ES is connected by 3 channels, one which goes in at K1, and so that's positive, and that gives you the K1 ES, and then 2 that drain out, K minus 1 and K2, and that gives you this term. And then when you rearrange that and you write it out as what you think is going to be a KD, but really is the KM, you show that KM is equal to K2 plus K minus 1 over K1. Okay, so all that's review. I don't want to spend too much time on it, but always do the units check often explicitly, and it's just shown here. And I just thought that would be good review too, because last time we did units, we saw first order rate constants have units of reciprocal time, and second order rate constants like K1 have units of inverse molar, inverse time, and you can see that when you do the units check it comes out in molar, and that's what we know what Km is. Okay, so we know that the units check out. All right, so bottom line is we have a derivation, we have an equation for Km, and then what I want to talk about now is kcat over Km. Okay, so all that's review. Feel like reviewed, everybody? Okay. All right. So kcat over Km is what's often called a specificity constant. And once again, it just wrote down the equation as well as the equation for velocity, which is on the preceding slides, and the equation for Km. And so now we'll go ahead and start to fill in, and we can say, what is the velocity equal to? Well, the one thing I can do is I can replace ES here with ES from the second equation. And you can see that ES from the second equation is equal to E times S over Km. So we'll go ahead and put that in. And so now in place of ES, I'll put in E times S over Km. So that's a really important equation. And it says that the velocity of the reaction, oh, that's nice and bright. The velocity of the reaction is equal to K2 over Km, or you could call it kcat over Km. I think I'm going to leave it as K2 for now, but it's kcat over Km times the concentration of free enzyme times the concentration of free substrate. And if you go back and look at lecture 1, the first thing we did was get that free enzyme the heck out of there because we don't know it, right? And we use, if you go back and look at the derivations, we do know the total concentration of enzyme, but we don't know E. So we did all sorts of stuff to get rid of it. And this is an intermediate step. But this is actually, in what we're doing right now, is our end game, not our intermediate step. That's actually what we want. We want to leave it. And it's important that we realize that that's free enzyme and not total enzyme. And also, this is going to be true under all conditions, because I didn't make any assumptions here or any limits. So this equation holds under kcat over km conditions, and it also holds under kcat conditions, because it's not total enzyme, it's free enzyme. And there absolutely no assumptions have been made. Okay? So, so this holds for all conditions kcat over km and kcat conditions. Although it would be much more intuitive to use it under kcat conditions. So with that in mind, let me see if I can figure out, I think this works, yeah. Okay. So if we grab this equation here and just write it over on the next page. But now let's pretend that we have a mixture of two substrates. Okay, we have substrate A and we also have substrate B. Now they're each going to have their own kcat over km. So this has to get like a superscript on it. And they're each going to have their own velocity as well. But to help you picture it, let's actually let's sketch out an Eppendorf tube. And in this tube is going to be free enzyme A and B, as well as some bound too. Okay. So if you compare these, what can you say about the concentration of free enzyme in these two equations? Nothing? It's going to be the same. So if we divide these equations, we can divide it out, because they're in the same tube, so they'll see the same constant. No matter what it is, it cancels. Okay? Very good. So that's the trick. This is almost always done in a ratiometric way. So, so what you want to do is divide these two equations. And I think I'll put B on top. We'll go ahead and write it, and then we'll draw the line through it. Like that. Okay. But we can also choose now this is getting more specific at this point, but we can choose to have the concentration of substrate B equal to the concentration of substrate A if they are in excess. So typical multiple turnover conditions. In other words, if E is limiting, then the concentration, and we can do that because we're in control of the experiment. We can add equal amounts of the two substrates. So I'll put initial here and initial here. And if that's true, then this equation reduces even further. Because now they'll cancel. So in other words, we don't want to give one substrate a head start, although remember that you can do that. And you know, like Josh in the experiments you guys are setting up, you try to do it so everything's there in equal amounts, so they have an equal chance of winning the race, and it may be that that's not true in the cell. One substrate might be much more concentrated than another. If that's true, then the competing rates is just the ratio of the kcats over km's, and that's true under all conditions. And that's a really important equation. And remember, that's true under both kcat over km conditions as well as kcat conditions. Let's see. So I jotted down a few notes. Yeah. So. I'm going to go back in this back one page for a minute. There's something I forgot to say, and that is that first off, I think we have space here. We can do this up in this space. We can look at the units. On kcat over km. And you know, one way to do it is to just take the equation, and we know that velocity is molar per second. And we know that these two are concentrations. So the units on this guy must be inverse second. What do I want to do with molar? Inverse molar. So what kind of a rate constant is it? Second order. Remember, second order rate constants have those kind of units. Okay. So people say, and I'll just say this in words because I'm recording my voice, and rather than writing, but feel free to write it, is that kcat over km is the second order rate constant for the reaction between free enzyme and free substrate. And that's working backwards from this equation that's highlighted in red. Look at that equation. Let's say you didn't have a mechanism. If you looked at that equation, you would say there's two things. It's a bimolecular reaction, right? Because we know if we had A plus B and we had them reacting, we'd see A and we'd see B, right? So we'd say it's a second order reaction between A and B. So when we look at that equation, you say that is the equation for a second order reaction between free E and free S, where the second order rate constant is kcat over km. So that's where that comes from. Even though you can't really write it down that way, I'm not all sorts of strange things happened up here with my my notes. But when we write it, we go back to oh, there it is. Okay, it takes a second to respond. Go back. When we look at this version right here, we don't really see a second order reaction between free E and free S, but that's how it works out mathematically, and so you can reverse it in your language. Yeah, Erica?
So is this dealing with like pre-steady state scenarios? Because Because under most cases,
yeah.
you wouldn't have much free E.
Right, right. So we're going to talk about it right now under conditions where there's lots of free E.
So like at the very beginning of the reaction.
No, it doesn't have to do with
Or
it
just
doesn't
like
have to do with time. It has to do with relative amounts of substrate. So
How they bind.
right. So if the substrate concentration is less than Km, then most of the enzyme is free at all times. But this equation even holds under other conditions too. It because no assumptions are made in deriving this part. So we can return to that idea. The other thing I wanted to say, as I already mentioned, is that this is an important relationship. If I can move that, because it's a situation that arises often where you put two substrates into the tube, like shown here, and you ask which one does the enzyme prefer. In fact, maybe I'll just go off on a tangent here for 1 second, and that is when you think of enzymes, there's really 4 characteristics that come to mind. I wasn't planning on doing this, but I think I'm going to do this. If you were going to take an enzyme and define it, I always think of 4 things. Do you guys know, when you think of enzymes, what do you think of? 4 characteristics of an enzyme. Not consumed. It's like a top 10 list, top 4 list. Thanks, Josh. Not consumed or not changed in the reaction. Anything else? Specific. Oh, that's a good one. Anything else? Sure. Speed, call it fast. Speed up a reaction. And the other is that, I'll just give it to you, is they tend to undergo multiple turnover. Okay. So they're not, first is not changed, and they're not, they can undergo multiple turnover. So ribozymes, since being a ribozyme person, ribozymes only fulfill number 2 and 3, generally speaking. Like single turnover enzymes, like a hammerhead ribozyme, for example, as it's found in nature, is consumed in the reaction, and it's not multiple turnover. And so some people, like say Squire Booker, for example, who's not gets hung up on that definition. We'll talk about that on another day. It's a non-issue, and I can convince you of that, I'm sure, or I can try to convince you of that. But the most important of the 4 are number 2 and 3, without a doubt. That they're specific and that they speed up the reaction. Those are the ones that are really chemical. Numbers 1 and 4 are really questions of engineering. You can always engineer a ribozyme to be multiple turnover. Those in my group know that. All you simply have to do is make a cut in the loop between where the substrate binds and its guide sequence, and then you can bring it in. It's not consumed. The enzyme's not consumed, and it becomes multiple turnover just like that. So, but it's always specific and it's always fast. And of those 2, probably the most important one is that it be specific. That enzymes, almost every reaction in our bodies, I think maybe without exception, is there's some enzyme that's involved, both to speed the reaction up and to make sure that it's specific. And so the stuff we're doing now is really important because specificity is such a key idea. And that's why this is called, kcat over km is also called the specificity constant. Okay. All right. So Now what Erica was kind of starting to get at is different conditions. And what I want to do, and I think is really valuable, is kind of give you guys some different ways to think about reactions. And I want to get into drawing free energy diagrams today because I think they're really useful. But the way I was thinking about it this morning is that I want to look at the limits. And so I want to actually look at these reactions under kcat over km conditions, even though that's not absolutely necessary, because the reason I want to do that is because it's more intuitive and it also makes it easier to draw the reaction diagrams. And we already did this back in lecture 1, so I'll go through it really quickly. If there's questions, by all means, stop me. But just remember that in the simplest way, we can write down the Michaelis-Menten equation. Is like that, and we can take two limits. And as soon as you see a plus sign, that's the clue that that's where you should go for the limits and compare S to Km. And so if we want to, I want to write this just one more time. Vmax is equal to K2 times E naught So you'll remember under kcat over km conditions, that's where the substrate concentration is low. And low is always a relative thing. Low means low relative to km. So let me write this slightly different. So in the limit that concentration of S is low relative to km, then we know that we can ignore S in the denominator, and then the equation reduces down to now notice that I have E naught in there, okay? But we know also under these conditions that E naught, it's always equal to E plus ES. But because the concentration of substrate is low relative to the Km, most of the enzyme is not bound up with substrate, so it's approximately equal to E. And so, in other words, under these conditions, V is equal to kcat over Km times the concentration of free enzyme times free substrate, which is exactly what we expect from what we derived on the previous equation. Okay. So I think I'm going to work on this. Let me just zoom all this down. So there's further limits that we can take within this limit, if you know what I mean, because we know that Km is equal to K2 plus K minus 1 over K1. We looked at that a few slides back, and it comes from an earlier class. So again, whenever you see the plus sign, you know that there's two limits. So the left term can be bigger than the right, or the other way around. And so so we'll go ahead and take those two limits. And limit 1 within the kcat over km limit is that, well, my limit 1, I let K2 be big. And we can see when that's true that the velocity is simply equal to K1 times E times S. Right? Everybody see it? where that comes from? I'll give you a minute to catch up. Just comes from here. If K2 is big, then the K2's cancel and the K1 swings up into the numerator. And then limit 2 will be the other way around. K2 will be small in comparison to K minus 1. And when that's true, now the it doesn't cancel, and so I get K1 times K2 over K minus 1 times E times S. So that's limit 2. So in other words, kcat over km in limit 2 is equal to this. And you can see it has the right units, right? Because K1 is bimolecular and the other two are unimolecular and they cancel. And then and here you can see that kcat over km, it's really simple. It's just equal to the on rate constant. So have people seen this before? Anybody know, been through this? It makes sense, but have you seen it before?
It just makes sense.
But it makes sense? Yeah, okay. So so the other thing to be mindful of is that K1 is the association rate constant here. And from collision theory, the fastest that two things collide under typical rates of diffusion is 10 to the 9th to 10 to the 10th per molar per second for K1. So that's the fastest that K1 could be. But it's never that big with enzymes. It's rarely that big. And so, so to have a productive collision, and you have a big enzyme, it has to find the active site, it has to go in the right orientation. If it hits the backside of the enzyme, it might not work, etc. And so that's the limit. But in practice, and it depends on the details, but at least in RNA, and I think in a lot of enzymes, it tends to be more on the order of 10 to the 7th to 10 to the 6th to 10 to the 7th. Now you may think to yourself, how could you ever measure anything that fast? But that's where the pseudo first order kinetics come in, because it's the you're multiplying it by two things, right? E and S, and so typically one of those is, say, micromolar with an enzyme, and so that reduces, when you do the math, that reduces the 10 to the 6th when you multiply it by 10 to the minus 6 down to 1 per second, and then that has a half-life of about 1 second. And that's no problem for rapid mixing methods. And if you use nanomolar amounts, you can get it down to hand mixing, down to minutes. Okay? So I used to think that when I first, I'm just saying that because I remember what I used to think when I looked at that. I thought, oh my, how can anyone measure anything that fast? Actually, it's pretty trivial to measure it that fast for a bimolecular. If you have a unimolecular that's that fast, that's another thing altogether. Okay. So oops, what did I just do? Oh, crap. Here we go, okay. This should work. Oh, I know what I'm doing. There we go, okay. So let's draw some free energy diagrams. And before we do that, I just want to remind everybody about the relationship between activation energy and rate constants, which you're all familiar with the Arrhenius equation. And I had to write down Arrhenius because I can never spell it. I think this is right. I looked it up on the internet today. It's right. Okay, everybody knows the Arrhenius equation. And so this is an activation energy, which is actually more closely related to an activation enthalpy and not necessarily an activation free energy. Now, one can also write these things out for free energies as well, but I'm just going to stick, maybe this summer, maybe not. We can talk about transition state theory where you write this in terms of delta G double dagger and then reduce it down. But for now, I'm just going to use the Arrhenius equation to keep it simple. And generally what people do is take the natural log. And so, so the only thing I want to point out is that I don't want to plot or anything like that, but just to point out that as the activation energy gets bigger, the rate constant gets smaller. There's an inverse relationship, and that's really all we need to worry about for today. So therefore, as you increase the activation barrier, you decrease the rate constant, and vice versa.
So that's multiplied, right? Not subtracted.
Here, it's subtracted.
No, it's multiplied. Oh, yeah, I got it. Oh, yeah.
Yeah.
Adding the negative.
Yeah. Okay, you see it? Yeah. Okay, that's fine. Yeah. So as the rate constant gets faster, the barrier is going to get lower, and as the rate constant gets slower, the barrier is going to get bigger. All right. So let's draw a few diagrams. All right. So back on this page, there were two limits. We'll start with limit 1, where k2 is bigger than k minus 1. Okay, we're going to start with this guy right here. And we already know that the velocity is approximately equal to k1 times e times s. So what people generally do is they'll draw something like this, and this is the reaction coordinate, and I'll probably only label the axis for this one time. And then this is some kind of energy or free energy. Okay. So, but maybe I should keep it as activation energy for now. Okay, and we start out with free E plus S, because in other words, this is simply this part. This is one state. Okay, so we're going over the barrier. That first barrier is the barrier for K1. And that has a transition state. Every step in a reaction has a transition state. So they all have a peak, a maximum that they have to go over. So we need it to go over something. Oops. And then start to come down. And this is going to correspond to the activation energy for K1. How do we want to write this? Let's write it like, oops. Let's write it like this. Okay? And now I have to decide, I've got a decision to make here on where what I want to do with this line. I stopped because now I've got choices. I've got choices about how far down I want it to go. So I could stop here, or I could stop even, or I could stop down here. Those are three choices. And because it's under conditions where the substrate concentration is low relative to the Km, most of the enzyme is not going to be bound with substrate. So we're not going to have we're not going to have this situation here, where ES is low in energy. That would only happen when we have tons of substrate, so that most of the enzyme is lower in free energy than the free enzyme. And that we said that's not the condition, so we don't want to do that. And we don't want to make it the same because we said that it's the other set of conditions where the concentration of substrate is low relative to Km. So it's going to go there. And so that's the first decision. Now the next, and let me stop there and say that this barrier here, these are supposed to go to the same height. Right, if this guy was the activation energy for, this is ES here. If this is the activation energy for going forward, then this must be the activation energy for going back. Okay, so now I have a choice with, everybody with me? Okay, now I have a choice with this guy. I can stop him here, or I could have him go all the way up there. And so this is now the activation energy for step 2. And we said that 2 is faster than -1. So if it's faster, that means the barrier is lower, because it's an inverse relationship. So that means I don't want this high barrier. I want this low barrier. And so I want to draw it more like this. And then this is the barrier for 2. All right, and that's the situation I have. And so if kcat over km is for the reaction between free E and free S, then free E and free S are over here, and the highest point that they see on the barrier, once they get over this mountain right here, it's all downhill, right? They'll get into here, and they're going to tend to go, once they get here, they're going to tend to go forward rather than going back, because going back is much harder. So for this diagram, that's the effective transition state, and you can see that that's for K1, and that makes sense in terms of what we expected under this limit. All right, so in order to get comfortable with it, let's just do the other limit. And that's where K2 is small compared to K minus 1. Okay, so in other words, I'm switching between this one to this one. And we said on the previous slide that when that was true, the velocity was equal to what? K1, K2 over K minus 1 times E times S. And so we can go ahead and draw the reaction diagram for this. So I go up, and then I know I need to stop here because I'm at subsaturating conditions. But now we know that 2 is slow compared to -1, so this barrier needs to be higher. So now it comes down like that. Yeah, Dan?
Is the end product lower in energy than the starting product? Starting material?
Depends on where you are in the reaction. So the height of, that's a good question, the height of this barrier, which is something we haven't even written in our mechanism here, but that's for going back this way.
So we haven't decided if that's bigger or smaller than K1?
Well, let's go back to K1, okay? So the height of the barrier for here has to do with the relative concentrations of E and S. So I haven't said this yet, but as I raise the concentration of S, that will raise this guy, okay? And because it'll effectively go faster from a pseudo first order point of view, which we haven't gotten to yet. But if that makes sense, then as we add substrate, what happens is this comes up to the point where it's here, and then it's all in ES. And that's what you expect, all the E to go to ES. So same thing with product. As product builds in, this will come up. But early in the reaction, there's almost no product because the reaction's just started. So under initial rate conditions, the concentration of P is so low that once it does release, substrate's almost always going to go on, so it's never going to go backwards. And so we ignore it, and we depict that in these diagrams by being way down really, really low. Okay. And so now you can see that if you're free E and S, you have to traverse the second mountain. It's not enough to get over the first mountain. You have to get over the first mountain, then you have to also get over the second mountain. And so that's why effectively you have in your kcat over km, you have all three of those. And so here, another thing to note is that this is an effective k-on. And it's much, much slower than those 10 to the 7th, 10 to the 6th things because we know that K2 is smaller than K minus 1. So we're multiplying K1 by something much less than 1. Right? This piece here, if you divide both sides of that equation by K minus 1, you see that K2 over K minus 1 is much, much less than 1. So you're reducing K1. So the on rate is really slow. So if you see a really slow on rate in your enzyme kinetics, much slower than what's typical, then it's in this is also called a rapid equilibrium. All right, because E and S come into equilibrium before it reacts. And that causes Km to equal Kd in this case, right? Because remember that. Let me shrink all this down and just make it a little bit smaller. So you guys will remember the definition of Km. And the flickering gets worse as you do more. And you can see here that K2 is small in the one on the right. K2 is small, so in this guy, Km equals Kd. And that's because it comes to rapid equilibrium. And K minus 1 is much bigger than K2. But over here, in this scenario, Km does not equal Kd. Okay, and in fact, Km is what? It's bigger than Kd. because K2 is bigger than K minus 1.
So what does that look like on everything K was
They all look the same. So in other words,
it comes to equilibrium before it reacts.
there's no way to tell these scenarios apart. They both follow, where's that equation? Yeah, they both follow this equation perfectly. So if you were to just plot it, you'd get a hyperbolic curve, you'd get a Km, you'd get a Vmax. You can't tell them apart. There's no way to distinguish them by standard experiments. So we can talk about how to distinguish them. You have to do pulse chase experiments and single turnover experiments to tell these two apart. Okay, so that's almost an hour. I mean, I can do one more slide maybe. We started a little bit late, and then okay, let's do one more. And then you can have a week to take it all in and go through it. It's getting more complicated, isn't it? I mean, but once you get the hang of it, it's really cool. And so, what I wanted to do was think about competing substrates. Okay, so in terms of free energy diagrams, and this is where it gets really powerful. This is what Mike Harris does in all of his publications. So, what did I do in my notes? I started out with, I can't even read what I did. I stitched those. Okay. We'll start out under kcat over km conditions, and we'll start out with rapid equilibrium for now. Like that. All right, so we know how to draw that right off the bat. That wasn't very good. Let me try it one more time. There we go. Okay, so let's say that's for A, and then for B, I'm going to do B in purple. All right, it's hard to see that. That wasn't a very good choice. Let me pick a slightly lighter shade of purple. It's like lilac. Okay, so what we can do is we can let a couple different things happen. So we're going to let A be the better substrate in all cases, just by arbitrary. So I'm going to say that kcat over km for A is going to be greater than kcat over km for B. So A might be the native substrate, B might be a competing one that's similar but not as good. And so there's a couple ways that this can happen. So one is that the K2 for A can be faster than the K2 for B. Another is that the Km's could be different because it's kcat over km. So Km for A could be smaller than the Km for B because it's in the bottom, right? That's what would make it better. Go ahead and draw that. And if Km is better, then that could be because K minus 1 for A is smaller than K minus 1 for B. Or it could be that K on is faster. So how do we draw all those? So in other words, if you look up there, there's three starting points, and they're all just showing A. exactly the same way. They're all rapid equilibrium, and they're all subsaturating substrates. So now let's come in with B and see if we can adjust it properly. So if in the first scenario here, then we know that K2 is going to be smaller for B, so that means it's going to have a higher activation energy. So we'll go ahead and draw that, and what we might do is put its activation barrier there. But we know that, we said that we assume that K1 and K-1 are unaffected, so we won't change those, and we won't change that. And so it'll end up looking, I'm going to try to offset it slightly so you can see the other one. It might end up looking like that. So now let's go down to this guy, and let's say we want to make, we want to affect only K-1. And we want to make the barrier higher for B. And so if I do that, I'm sorry, if I do that, I can't do that, okay? Because if I do that, I'm also going to change K1, and I don't want to change K1. So the other way I can do it would be, let me get rid of that first guy. Anyhow, let me go back. I'm sorry, I misspoke. All right, let me just go back. If I do this, what I actually do is make K-1 smaller for B. And that's even the opposite of what I want to do. So I definitely don't want to do that. I want to think out loud so you guys can see the thinking here. I could do that. That would make K-1 faster for B, but it would also make K1 faster because they pass through the same transition state. So I don't want to do that. So an alternative, instead of lowering the barrier, is to raise the ground state. So I could do that. But if I do that, I also affect K2, because I make K2 faster, because I've lowered the ground state, which is common. So I can raise the transition state at the same time. And that's generally what people do. And so if you look at it now, that diagram right there should only change K-1, and it should make K-1 faster. So the same offset that I did in that ground state I did in that transition state. So that's a scenario for that. And then lastly, let me see if I can figure out a way just to change K1. If I want to change K1, the easiest thing to do is just to change the ground state. Then I don't have to worry about monkeying around with any of the other rate constants. I'll try that again. So those are the three scenarios, and then the question is whether or not it's the purple one is actually slower than the other ones in all three scenarios. And so remember, it's always at least in these cases, it's the reaction between free E and S, which is here, and the transition state, which is here. And so you can clearly see that the barrier for A is there, and the barrier for B is there. So B is going to go slower, right? I'm just going across to the barriers like this. And you can see that the same thing is going to be true here. And that also the same thing is going to be true here, but for a slightly different reason. Okay. So when you have competing substrates and one goes faster or slower than the other, it can be for different reasons microscopically. And not only that, on top of this, you can have changes in the rate limiting step. I assume that the rate limiting step stayed as the second barrier in all of these. But you can imagine a scenario where that is no longer true, where if you raise the barriers and start to raise and lower the barriers, you can switch from the second barrier being rate limiting to the first barrier being rate limiting. So if you want to do some practice, I'm going to stop because I know we all have stuff to do, myself included. But and I have this terrible feeling I'm supposed to be somewhere at 1. Par for the course. But what you can do is repeat this whole slide that we just did, but do it. This should come up. Do it for the one on the lower left. Okay, and what you'll see, you can almost do this in your head, right? If we monkey around with this barrier, it's not going to matter, is it? Because this is the rate limiting step here. So you always want to be in rapid equilibrium to have the greatest amount of specificity. So if we monkey around with this, or we monkey around with both of these at the same time, it's not going to matter. If we monkey around with this one, it is going to matter. It's not going to matter unless we raise it to the point where it becomes a new rate limiting step. So you can get changes in rate limiting step, and those can affect things as well. All right. Class dismissed.